We previously said that temperature is the average kinetic energy of a system. Today we're going to refine that definition a little bit because it turns out that molecules actually have three types of kinetic energy that's relevant to this discussion. The first is the kind of traditional sense that we're used to. Something moves from point A to point B, has a velocity. That type of kinetic energy is called translational. Translational kinetic energy. And what that means is I have, let's say, a molecule looks something like this. We can model it as two spheres, 2 point particles, connected by a spring. So translation is I physically move it from point A over to point B. And if it's moving, it has kinetic energy. But something else this thing can do, since this is a spring, they can bounce off of each other. Okay? And that's vibrational kinetic energy. And the final type is, okay, I have these two things connected like this, I can move them like this. I can rotate them. So the last type of kinetic energy is rotational kinetic energy. Okay? Now, not all phases of matter exhibit all three types of kinetic energy. The molecules in a solid are so tightly packed together that they're not really able to rotate. As such, solids will only have translational kinetic energy and vibrational kinetic energy. The molecules in a solid will only have those types of energies. And it turns out that temperature only cares about one of these. Temperature actually only cares about translational kinetic energy. And we're going to refine our definition and say that it's the average translational kinetic energy. And then one more important point to bring up before going into our discussion is that thermal energy, which is transferred when you have heat, right? Heat is the transfer of thermal energy. Thermal energy will be equally divided between all available modes of kinetic energy. So thermal energy, right, makes stuff move. It makes the molecules move inside a substance. If I have all three modes available, if I have a liquid or a gas, then that thermal energy, if I heat something up, will be split between translational, vibrational, and rotational kinetic energies. However, if I'm missing one, it'll be split between whatever's available. So let's look at a situation where we have two liquids and a solid. And I'm going to mix stuff together, and we're going to see what happens if we heat some things up. So I'm going to have liquid 1, liquid 2, and a solid. And I'm going to say that we know liquids are going to have all three types of kinetic energy. So they'll have translational, they'll have vibrational, and they'll have rotational. But a solid, on the other hand, is going to be missing rotational kinetic energy. So we'll have translational and vibrational, but it does not have rotational. Okay? So, now what I want to look at is say that liquid 1 is hotter than liquid 2. And let's say that it's hot enough such that it's going to give 6 units of thermal energy to liquid 2. We mix them together and it releases 6 units of energy. So those units of energy when released, when something releases thermal energy, that's also going to be split evenly among the modes of kinetic energy. So I'm going to have 2 heat arrows, we'll say, coming out of translational, 2 coming from vibrational, and 2 coming from rotational. Now when liquid 2 sees these 6 heat arrows, these 6 units of thermal energy, it doesn't care where they came from. All it sees is, oh, I have 6 units of energy. And it's going to split those among its available modes. So 2 will go into translation, 2 will go into vibration, and 2 will go into rotation. Okay? Straightforward. When we put a solid into a liquid, let's say that liquid 2 is hotter than the solid, and let's say that it's at the right temperature such that it too will give 6 units of energy to the solid. So again, it's going to have 2 emerging from translation, 2 from vibration, and 2 from rotation. Okay? So the solid sees, again, sees 6 units of heat, 6 heat arrows. And it says, well, I need to split these among my available modes of kinetic energy, and it doesn't have rotation. So this means that 3 units of energy are going to go into translation, and 3 will go into vibration. So what this is saying is that if I put the same amount of heat into a gram of a liquid and a gram of a solid, solids, generally speaking, will heat up more. Because this is what temperature cares about. Only translation matters when we're considering temperature. And you can see that even though we're still putting 6 units of heat into a solid, more is going into its translation, and therefore its temperature will go up more. And this takes us to the idea of specific heat capacity. This should really say specific before it. So we're going to be talking about that. So, specific heat capacity, let me kind of clear some stuff off here. I will define as the amount of heat per unit mass, or the amount of, I guess, heat is transfer of thermal energy. So we'll say the amount of energy per unit mass, whether it be a gram or a kilogram or whatever, required to raise temperature by 1 degree Celsius. Okay? So you can see, now we want to think about, do solids or liquids, generally speaking, have a larger heat capacity? Well, we know that the amount of energy needed to raise the temperature of a solid by 1 degree is less than the amount of energy needed to raise a liquid 1 degree. Because it's going to have more energy going into translational mode into solid than there will be in a liquid. So the heat capacity, we use C for heat capacity. So this heat capacity of a liquid is going to be greater than the heat capacity of a solid. Water actually has a very, very large heat capacity. Among the most common substances, it definitely has one of the largest heat capacities, which is part of the reason why the oceans are such good moderators of temperature, because it's able to absorb a lot of heat, a lot of energy before its temperature changes. So it tends to kind of lag behind in the seas. If you look at the winter and the summer on the east coast of the United States, the temperature of the ocean is going to lag behind the temperature of the air when it comes to looking at seasonal changes. And it's because of the large heat capacity that this happens. So, how do we use this to actually figure out things about energy and about temperature? There's an equation that we're going to use, which is Q is equal to mc delta T. So, I'm going to make a little table here. We're going to say, we're going to have our symbol. We're going to have the meaning of the symbol. We're going to have our units. And I think that's it. So our first symbol, we're going to have Q. So Q is energy. Energy, heat, that type of thing. So if I ask you how much energy does something take, you're going to be looking for Q. The units of Q, you're going to see a few. You'll see joules, because, let me put more generally, the units will be energy, which typically will be joules, or calories with a capital C, and here's the terrible thing, or calories with a lowercase c, where capital C cal is equal to 1,000 lower c cals. And the nice thing about calories is that it's calibrated well such that the heat capacity of water, if you're looking at calories, is 1 calorie per gram degree Celsius or Kelvin. which is nice. But generally, and when I'm doing stuff, you'll typically probably see me using joules. This big calorie is also called a kilocalorie. So we just write that kcal. And let's see, the type of calorie you're burning or you're getting from food is the big C calorie. That's what you're eating. So, good. So that's Q. M is mass, and unsurprisingly, we'll have units of mass, which will manifest as either grams or kilograms. C is specific heat capacity, and has units of energy divided by mass times temperature. And I think about that makes sense. How much energy is needed to raise some unit mass 1 degree Celsius or Kelvin? Okay? And you will see typically either joules per gram, Kelvin. Whether it's Kelvin or Celsius doesn't make a difference, because the intervals between 2 degrees in Celsius and Kelvin are the same. They just start at a different baseline point. Celsius starts at -73.15, Kelvin starts at 0. But the rungs of the ladder as you're climbing up the degrees are the same for both. So joules, gram, Kelvin. You might also see a K here, kilojoules per kilogram Kelvin. And you will also see calories per gram Kelvin, or Celsius. Okay, and that leads, our last one is delta T, which is the change in temperature, which is our final temperature minus our initial temperature. We'll have, it means temperature, well it actually means change in temperature. So change in, and it has units of temperature. Okay. So this equation is going to govern, we're going to use it a lot, it's going to govern how things warm up. How things warm up and cool down, how much energy it takes to change temperatures and things like that. And the great thing about it is we can also use it to determine if we mix stuff together, what's the final temperature of that mixture going to be, or what's the initial temperature of the mixture, etc. So this is everything for specific heat capacity, and if you're interested in seeing some example problems, then go to the next video.